is Sean McCusker. I'm a second-year MERP student.
My name is John Levy. I'm an assistant professor in urban studies and planning.
Jennifer Dill, I can now say associate professor in urban studies and planning.
Ben Silke, visiting student from Germany, Dresden University.
Shoaib Khan, senior, civil engineering.
Leslie Barwin, third year urban planning student.
My name is Matt Burnell. I'm a first year.
Chris Monsieur, faculty member in civil environmental engineering, and now I can say assistant professor.
Eric Rundle. I'm a second year MERP student.
I'm Hannah Capel, and I'm a first-year MERP student.
Nicole Prihoda, and I'm a first-year MERP student.
My name is Nathan. I'm a journalism major taking post-bac studies in transportation planning.
Daniel Livers, community development major.
Computer science.
Kristen Tufte, research associate, civil engineering and computer science.
My name is Holly Stout. I'm an economics major, and I'm graduating next term.
I'm Delatore, graduate student in urban studies. I work at the Institute on Aging.
I'm Amanda Smiller. I'm a hopeful graduate for the MERP program.
All of you, and very good work on the microphones. Usually Jennifer's the one who will remind you if you don't, so better watch it. And I guess I should note that John Glebe, Professor Glebe, is a new faculty member, and so we're very excited to have John here. Jennifer recently was promoted and tenured at Portland State, which is no small accomplishment. And Chris Monsieur was recently, in a sense, promoted. He's now an assistant professor in civil and environmental engineering. So three very exciting people sitting over in that corner. Speaking of exciting people, we're really happy to have Dr. Yibing Wang here today, and I'll give a brief introduction and then we'll move right into his seminar. He's visiting us from the Dynamic Systems and Simulation Laboratory at the Technical University of Crete in Chania, Crete, Greece. And I've never been to that place, but it's my goal to one day visit his lab. And so Yibing is on, in a sense, a U.S. tour right now. He visited MIT and Purdue, and he's stopping here at Portland State on his way to UC Irvine and UC Davis before he returns to Greece in a week or so. And today he's going to be talking about some work he's been doing with his collaborator, Marcos Papageorgiou, and the title is A Generic Approach to Real-Time Freeway Network Traffic Surveillance. Just a little bit about Yibing's background. He has a BS in electronic engineering from Sichuan University, not in Greece. An MS in control engineering from Chongqing University, also not in Greece. And his PhD is in control engineering from Tsinghua University in Beijing, which I believe is the #1 university in China, if I'm not mistaken. So, with that, it's all yours.
Thank you very much for the introduction, Professor Bertini, and good morning, everyone. It's my great pleasure to be here to have this presentation and to exchange some ideas with my colleagues. So now I start. This topic of the presentation is about a generic approach to real-time freeway network traffic surveillance. Perhaps I should mention I have a somehow strong Chinese accent when I speak in English. So if during the presentation you feel anything unclear, please don't hesitate to let me know so that I can give some explanation. Actually, this work was supported by the European projects, which was funded by the European Commission. The work was done by me, Professor Papageorgiou, and Dr. Messmer in Germany. I would like to first give a general idea about freeway network traffic surveillance, real-time freeway network traffic surveillance. As we can see, we have two blocks which represent the same freeway network. On the top block, we can see we have a freeway network in general. the freeway network is installed with a number of traffic detectors. And here, each line node represents a traffic detector. As we know, the detector only provides some local information about traffic speed, traffic flow, and traffic occupancy. But on the other hand, if we are traffic operators in the traffic control center, let's imagine only have the local limited information, it is not enough. We would like to have such a complete image, meaning we would like to know what happened for the whole freeway network that the traffic control center is currently supervising. So here, different colors of the links represent different kind of traffic situation. For example, free flow condition, dense condition, and congested condition. We can imagine simply based on a limited amount of noisy local traffic measurements, it's not so easy to have such complete image. This kind of complete image should be updated dynamically in real time, for example, every 1 minute. So recently we have developed such a tool, which is called Renaissance. This tool can deliver such a complete image at a time ratio of about 1 minute. Every 1 minute we deliver a new image based on limited amount of local noisy traffic measurements. We call this task traffic state estimation, meaning we can estimate speed, flow, and traffic occupancy for each location where no detector is installed. So this is a very, we believe this is very significant work, especially in the case if the network is sparsely installed with the detectors. Okay. Except the traffic state estimation, actually this tool can also perform a number of other traffic surveillance work. For example, traffic state prediction, travel time estimation, travel time prediction, queue tracking, and also a little bit incident alarm. I will explain more clearly later. So once we have such information, first of all this kind of real-time information can be given to the traffic operator for real-time decision making. Also, this kind of information can be used for further operations for the freeway network, for example, route guidance, run metering, speed limit control, and so on. But within this work, we focus on the task above the blue line. So that's a general idea of real-time freeway network traffic surveillance. Following such an overview, I will quickly describe the mathematical model we use, and I will introduce the addressed real-time traffic surveillance tasks. And then I will focus on real data testing of the traffic state estimation task. This task is the major task of the whole tour. Afterwards, if we still have some time, I will present some simulation testing for the other traffic surveillance tasks. Then finally, an outlook is given. So the mathematical model, actually our mathematical model includes two parts. The freeway network traffic flow model, based on the traffic flow theory, and also real-time traffic measurements model. This is based on the electronics of the measurement devices. First, the network traffic flow model. As we know, any freeway network actually only includes two kinds of elements. The links, which represent freeway stretches, and the node, which represents the bifurcation location, on-off ramp location, and so on. So that naturally the model, the traffic flow model, includes two parts, the link model and the node model. For the link model, if we have a long freeway stretch, we define it as a link within the model. We separate the link into a number of parts. We call it a segment. So each segment has a length of about 500 meters. So in order to describe traffic flow dynamics within every 500 meters, we use our model based on two variables, the density and the speed of the segment. The density means how many cars are there in the segment at each time moment. That's the density, the number of cars within the segment. The speed is the average speed of all the vehicles within one segment at each moment, which are those variables are updated dynamically. So based on these two variables and also some boundary variables, we can have our mathematical model to describe traffic flow dynamics of the segment. So once we have such segment model, then the whole link model actually is just a chain of segment models interconnected with the boundary variables. So that's a general idea. First segment model, because the link has a number of segments, then we have just the whole model. So this is actually the mathematical description of the segment model, which has we have a conservation equation, we have the transport equation, we have speed equation, we have fundamental diagram. So here I think for the moment I'm not going to the detail. After the presentation, if you are interested in, then we can come back. The point I believe is if the results are interesting, then people would feel interested in the methodology. Otherwise, the methodology itself doesn't make sense. So let's first focus on the results. If you like the results, then we can talk about the methodology. So within the fundamental diagram, this is important. We actually have 3 model parameters: free speed, critical density, and capacity. All these parameters are not only the parameters in terms of mathematics. Each parameter has its own clearly physical meaning. For example, free speed. What's a free speed? Free speed is when we drive. Our driving behavior is not influenced by any car in front. That speed is a free speed. Free speed, of course, is kind of mean speed because everyone has a different speed. Although if there is no car influencing us in front, but it's kind of mean speed, meaning only when the traffic flow is not very dense, the space between car to car is relatively big, then we can drive in the free speed. That's a free speed. Capacity is the maximum traffic flow that can be reached along a freeway stretch, that maximum flow. Then once such flow is reached, the corresponding density, I mean the number of cars along the freeway, that's critical density. So this figure actually gives the physical meaning of these 3 parameters. These 3 parameters are very important in order to use such any kind of traffic flow model actually. Just now I introduced the link model. Now of course we have node model. It's kind of very simple, traffic flow reach a node via a number of entering link and leaving a node via a number of leaving links. So the idea is very simple. So now actually the whole model includes a number of variables. For example, the density and the speed of each segment, and the original flow and the original speed, and the destination density, the turning rate as a bifurcation node, and exiting rate as off ramp, and so on. We call these boundary variables. Then we have some model parameters like free speed, critical density, capacity. So if we define some vectors, to include these variables, then actually we can express our model in such a very compact state space form. Then if we do some simple transformation, we can even further we can write the model in a further compact form. So that's the traffic flow model. For the measurement model, it's very simple. The idea is the following. The flow measurement is from the detector. The flow measurement is equal to the real flow plus measurement noise. The speed measurement is the real speed plus the measurement noise. That's a measurement model. Also, the measurements can be written as a function of the flow and the speed, can be written in such compact form. So then, actually, we got such a compact form of the model. We have the traffic flow model, we have the measurement model. So that's a model. Now I will talk about our traffic surveillance task. What kind of traffic surveillance task we want to consider. Just now, actually, I have already mentioned we want to consider traffic state estimation. Except this, we also want to consider traffic state prediction. Just a moment. Q-tail head length estimation and prediction and so on. So for traffic state estimation, just now I already mentioned, it means we want to estimate flow speed density for any location where no detector is installed. But this work is done based on the measurements from the location where detector is installed. Actually, it's kind of information reconstruction. Based on incomplete measurement information, we want to construct a whole complete image for the whole network. So since our model is such kind of nonlinear dynamic model, so in mathematics, for such kind of model, to do the state estimation, it is very straightforward to use Kalman filter. I don't know whether you are familiar with the Kalman filter, so I may come back to this detail, to this point in details later. And the major idea is following. We take the measurements. The measurement goes through this mathematical tool. The tool delivers the estimation results. For the travel time estimation, because we can estimate traffic speed for each segment along a certain route, so then the travel time estimation is just simply calculated based on the traffic speed estimation, so which is a kind of very straightforward calculation. For the Q head tail length estimation, the idea is quite simple. For example, imagine if we say we have many routes, so we want to know whether along this route is there any congestion or not, is there any queuing or not. The idea is the following: because we can estimate along any route the speed along any route at a spatial resolution of about 500 meters, then actually we can display the speed over the distance. So for example, we have such a displaying. For example, because we can estimate, we know that's over distance. We know every 500 meters what's the speed. We display it. If we define a kind of threshold, for example, 4 kilometers per hour, we say when the traffic flow speed is lower than 40 kilometers per hour, we say there is a queuing. There is queuing, which doesn't mean the traffic flow was not moving. It is moving, but very slowly. If we take let's say, a helicopter, if we look from above, from the sky, we can see it is a queuing because the car are moving very slowly. So we can use any threshold. If we say that's a threshold, for any segment with the speed lower than this threshold, we say that's a queue. Then, of course, we know where is the Q head, where is the Q tail. If this is the moving direction, then accordingly, we can simply calculate what's the Q length. Of course, this is depend on the threshold. So that's a general idea of the estimation task. For the prediction task, it's the other kind of story. For prediction, for example, for traffic state prediction, meaning we want to predict speed, flow, and density, and so on. For example, we are at the current moment. We want to predict for a certain location in the future, in the next 20 minutes, what will be the speed flow for a certain location. That's a prediction. It means to predict into the future. We don't know what will happen, but we want to predict. We want to use our model to predict. That's a predict. If we can predict the traffic speed, then we can also predict what will be the travel time along a certain route. For the same idea, if we can predict the speed, then we can also predict what's the queue in the future. Yeah. So that's a general idea. So this is actually the functional structure of this tool. As we can see, the tool has a number of modules. Each module corresponds to certain traffic surveillance tasks. We have real-time input. We have a lot of user options. Any tool offers a number of options so that the user can decide how to use the tool according to the exact specific user needs. Then, of course, the tool can produce a number of tasks, actually a lot of data files. And also we have a GUI, a user interface, user graphic interface, which can visualize the real-time traffic surveillance results. I have some examples later you can see. So I quickly go through the general idea of this tool and also the tasks we would like to do. So now it may sound a little bit abstract. So via a number of real data testing, the things may become more clear. So the first task is the traffic state estimation, the real data testing of the traffic state estimation. As I said just now, we use the extended Kalman filter to do this work. The extended Kalman filter is a model-based tool, meaning in the Kalman filter we have our mathematical model, just now I already introduced. And also the real-time measurement is used. based on the both model and the measurements, we produce the estimation. Okay, we just want to see whether such kind of estimation is accurate. We have to evaluate whether it is accurate. So since the model is involved in this tour, then it is important to decide how to deal with the model parameters. Just now I said we have 3 parameters: free speed, critical density, and capacity. As we know, these kind of parameters are different. It's from freeway to freeway. For this freeway, the free speed, critical density, and capacity are those values. If we turn to the other freeway, the corresponding values will be changed. There is no constant values. Generally speaking, traditionally, even until now, these kind of parameters are identified via so-called offline model calibration, meaning you have a model. Only the model structure is fixed, but the parameter values are uncertain. How to define the parameter values? We have to take a lot of real data from a certain motorway. Then we use a certain mathematical approach to find out what was the best parameter for this freeway, which means corresponding to this kind of real data. Whenever we do the same work for the other freeway, we'll have to take other data from that freeway. Then we'll get different values. So that's the general way is being done. Also, we are talking about macroscopic traffic flow model. Actually, now for the macroscopic traffic flow model, I mean car following model, there's a lot of this kind of model calibration work, because that kind of model may have 6, 8 parameters. Here, the macroscopic model only has 3 parameters. Actually, it's relatively easy, but still has a lot of problem, because first of all, this calibration is very tedious. Means in calculation is very tedious, time consuming. Second, once we get some value for this freeway, whenever you do the same work for the other freeway, you have to redo all this kind of calibration work. And also, even for the same freeway, these parameters are not constant. It may change according to the environmental condition. For example, today is very sunny outside. For a certain motorway close to Portland State, we get the corresponding parameter values as those. If tomorrow it suddenly rain, under raining conditions, this kind of parameter definitely will change. For example, the free speed, we can imagine, without rain, we can drive 120 kilometers per hour. I mean, when the traffic flow is relatively low. But with the same traffic flow, if it is raining, definitely the free speed will go down. So that's why the offline model calibration is not a good way. It's not very flexible. And also, if under the same weather condition, with incident or without incident, these kind of parameters are again not constant. With the incident, for example, we have a 3-lane freeway. Suddenly, 2 cars knocked at a certain location, and one lane is blocked. It's blocked temporarily, and there is a local bottleneck. Then the capacity there, the maximum traffic flow there can be reached. The maximum flow can be reached at the incident location will definitely go down. So the parameters you see, they are not constant. So we believe offline model calibration is not a good way. We would like to do online model calibration. So the online model calibration, or we call it online model parameter estimation, meaning we estimate flow speed and these model parameters simultaneously. So we don't need any offline model calibration. So if you remember just now, in the vector x, this is what we are going to estimate. Actually, it includes flow, speed, and the model parameters. So all the variables are estimated simultaneously. That's the ambition. That was our original ambition. So that's why the first real data testing, via this real data testing, we want to see whether we can avoid offline model calibration, whether we can be adaptive to the changing external condition, whether we can enable the incident alarm via online model parameter estimation. So now let's go to some real data examples, which can show you something more clearly. This is the freeway close to Munich in Germany. On the top there, that's the Munich airport. and here is the boundary of Munich city. So this freeway is very heavily congested in general. We did our testing in the part of this freeway. So here we have some side pictures. As we can see here, we have such a freeway stretch of 4 kilometers about. So there is on-ramp at the upper boundary of the freeway. So as we can see, we have 4 detectors installed around the freeway. That's loop detectors, meaning the loop detector underground. It is put underground. So that's the traffic flow direction. We see we have such flow measurements from downstream, from the middle measurement location until the upstream measurement location with the 3 different colors. That's a flow. And we can see we have speed measurements here. We can see the right curve, that means speed first drop. At the beginning is about 90 kilometers per hour. It dropped to about 20 kilometers per hour. First, the right curve, this means the downstream location. Then the blue one, then the black one is the middle location. Then the blue one, that's the upstream location. From this speed drop sequence, we can see there was a heavy congestion coming from downstream, which first reached the downstream location. That's why the first speed drop was measured at the downstream location. Then, with the congestion propagating to the upstream, it was measured at the middle location, then measured at the upstream location. This is a general way when the traffic congestion propagates. Once some location, the congestion is created, the congestion propagates to the upstream. We have such experience when we drive, right? So this congestion coming from the downstream. We want to evaluate whether our traffic state estimator can work accurately. So the evaluation plan is the following. You see, we have 4 kilometer stretch. We separate the stretch into 8 segments. Each segment has about a length of 500 meters. Then we feed our estimator with the measurements from the boundary. Right. From the boundary. We only use the boundary measurements. We want to estimate speed, flow, and occupancy for each segment. Since we also have a detector in the middle, right? The measurements from this detector was not used to feed the estimator. So that's why we can compare our estimation for segment 4 with the measurement here. If the results are good, this means the estimator works well, because this kind of comparison is objective. The corresponding measurements that are used for evaluation were not used by the estimator, right? So since just now I mentioned the model parameter estimation, so we always combine the two work together. First of all, I do such a kind of testing. I want to see whether the model parameter estimation has to be estimated online. I choose through groups of model parameters. So I will see free speed, critical density, and capacity. 3 groups of. Meaning I will run the estimator 3 times. Each time with these parameters fixed at these constant values. I want to see what will be the results. So that's the result. Meaning, if we don't do anything for the model parameters, if we will use constant model parameters, only with the first group of model parameters, the estimator works well. Okay, here the right curve represents the real measurements. The black, the green, and the blue represent the corresponding estimation results. Okay, only with the first group of model parameters, the estimator can work well. This means what? Means the following. If we want to keep the model parameters constant in the model, these model parameters has to be identified very well. You cannot blindly specify some model parameter values. If we do so, then the results are simply not good. That's why we say if we don't do anything for the model parameter, we don't do anything for the model parameters online, these model parameter values has to be offline identified well. That's why a lot of offline model calibration work has to be done. These results actually based on the parameters from the offline calibration. All other parameters was blindly given by me just for testing, meaning only this group this group parameters was from the offline model calibration. I did a lot of this kind of tedious calibration, which is very time consuming. Those parameters, as we can see, very different from them. I just, for the testing purpose, I specified them arbitrarily. But this gives us a strong indication, right? But now, with online model parameter estimation, meaning I don't do offline calibration, I estimate all the parameters online. But in this case, I still use these 3 groups of parameters, but use them as the initial values. With online model parameter estimation, the parameter can change automatically from the initial values. Then we want to see what will be the results. Again, the same 3 group of parameter values at the initial values. So that's the results. For example, this is free speed. We start with 3 different values. That's the capacity. We start from different values. That's the critical density. We also start from different values. With the same mechanism, online model parameter estimation, each model parameter estimates finally goes to the same value, although they start from different values. Why they can go to the same value? Because the real model parameter information actually is already contained in the real measurements. It is driven by the real measurements. The estimator is driven by the estimator. So with the time passing, the real value is identified. Real parameter value is identified regardless of what will be the initial value. So this means with online model parameter estimation, with the time passing, the real value can be identified. And also this real value, the real value is not sensitive. Whether a real value can be reached, this is not sensitive to the initial value. So this is very good. Meaning, actually, in general, traffic operators, traffic engineers at the site, working at the site, they don't have very accurate knowledge about model parameter values. Although they work every day for a certain site. But if you ask them what would be free speed capacity for that site, they may not know. So this gave them the convenience. They can specify initial parameters relatively blindly. Then they just run the tour. The tour will help them automatically to find the real value. Then the question comes out. Once such convergence is reached, what will be the speed and the flow estimation results? That's our focus. So that's the speed estimation results. And this is the flow estimation results. Okay, so we may come back later if some question would come. The second test example is along the same freeway stretch. Actually, the one just now I presented is from this on-ramp until the end, but the current one is longer than that. This is an interesting test example from February 11th, 2004. Okay. As we can see, this is a 24-hour data from midnight until midnight. Midnight until midnight. So here we have speed and we have flow. Okay. The interesting example, it is an interesting example in the sense we can see from midnight, 0 o'clock, until early in the morning, 6 o'clock, 7 o'clock, there was a clear speed decrease, right? Clear speed decrease. But at the same time, the traffic flow was very low. So then we would like to ask ourselves, why in the night there was almost no flow, but the speed goes down clearly. And the speed here is even lower than speed here, and here actually corresponding to the afternoon peak period. So this was a little strange to us. And for this reason, we conducted the Munich Traffic Authority. We found out with their help that day from somehow 10 o'clock in the night until 7 o'clock in the morning, in the whole Bavaria area, including Munich, there was a strong snowstorm. So then it became very understandable, meaning due to the heavy snow covering the freeway, due to the strong wind, the driver was not able to drive fast, although at that time there was not much traffic flow, right? So this reflects the impact of the weather condition on the traffic flow characteristics. Now, with the model parameter estimation, we ask ourselves, for example, with the free speed estimation, can we identify such kind of impact? Okay, if we can identify, then how about the free speed? How about the speed estimation? Actually, we got such work with online model parameter estimation. That's a free speed estimation. Clearly, there was a free speed drop. It was identified with the real data. And this is the speed estimation with online model parameter estimation, the black curve. And if we keep the free speed as some constant values, then simply the speed estimation cannot track such kind of speed drop. Because if we keep the free speed at a constant value, it's like we tell the estimator forget the external condition. The free speed is constant. But actually, in this case, the free speed was not constant. It was influenced by the weather condition. So you see, the free speed decrease, the free speed drop was clearly reflected in the real measurements. That's why, by use of the real measurements, the tool, the estimator can identify the parameter change involved. So that's the second example. Via this example, we want to show how the estimator, via using online model parameter estimation, can handle the traffic flow characteristics under weather condition impact. And we have the third example. The third example is the incident example, which was from April 18, 2004. That's 24-hour flow measurements, 24-hour speed measurements. As we can see, we have speed drop to almost 0 kilometer per hour, and we have a flow drop, which dropped to also 0. Whenever we have a flow drop to almost 0, this means incident, meaning there was something so that the flow was not moving. This can happen only under the instant condition. But if we have a very low speed, this doesn't mean something. This could be due to a congestion. But whenever we don't have flow, this means instant. So we would like to see how is the performance of our estimator under such instant condition. Actually, I did the data analysis. So the general situation is the following. That's our freeway, from upstream to downstream. Okay, at this detector, okay, you see the whole stretch. I mean, different types of detectors are involved into this test example. Here, at this detector, the speed doesn't change. Flow dropped a little bit. Here, both speed and flow dropped considerably. Both speed and drop sharply. And here, speed doesn't change. Flow dropped sharply. So even without traffic engineering knowledge, we can figure out. Here, both speed and flow dropped sharply. Here, speed doesn't change. Meaning what? Meaning something happened in between, right? That's why at the downstream of the incident, the speed doesn't change. But no flow coming from the upstream, so the flow dropped a lot. But at the immediate upstream of the incident, both speed and flow dropped sharply. Then the congestion propagate until very upstream, then the speed almost was not too much influenced, because there are also off-ramp. A lot of car actually goes out because they saw downstream a lot of congestion, and a lot of cars choose not to use the freeway anymore at that moment. So that was an incident. So there are some explanations based on the fundamental diagram, so I'm not going to the detail. And actually, this is our critical density and capacity estimation results. As we can see, during the time period with the incident, clearly there was a capacity drop identified, critical density drop identified. Indeed, because the flow was 0, so the capacity was not 0, but the capacity was very low. Capacity drop, right? And if we display the derivative of the of both curves, we have these two figures, the derivative. So then we can see during the around the incident moments, there was a very strong impulse, right? So the impulse can be used as a kind of incident alarming signal, meaning the traffic operator, whenever the traffic operator see something like that, this means something very abnormal has already taken place. So maybe some further measures should be taken. So that's an incident example. Then we also have the corresponding flow and the speed estimation results, which looks good. So actually we have already demonstrated, yes, with online model parameter estimation, first of all, the offline model calibration can be avoided. And also the estimator can be adaptive to the external condition. Also some preliminary evidence, we got some preliminary evidence that incident alarm could be issued. And finally, I would like to mention within the show and the testing example, the detector spacing used, meaning along the mainstream of the freeway, the distance between the detectors used was 4 to 7 kilometers, which is very long. Generally speaking, if we look at the literature, the detector spacing they use normally is less than 3 kilometers. If we can use detector spacing like 4 to 7 kilometers, meaning much less number of detectors are really needed. This means we can do the job with a very sparse information. Then this means a lot of money could be saved from the detector installation. We don't need so many detectors. Yeah. If the detectors have to be installed very sparsely along the freeway, first of all, the maintenance is very difficult because a lot of detectors may be putting underground. Once something happens, you have to open the pavement. That's very difficult work. But with a less number of detectors, the maintenance becomes easier, and also the installation cost, also the energy support, everything becomes easier, and a lot of budget, a lot of money could be saved. So, yeah, actually, 3 months ago, we also applied this tour to a freeway of 50 kilometers in South Italy, which is a hometown of, old hometown of Professor Bertini. Yeah. So this is another interesting example. So I will quickly go through this example. So this is South Italy. Here is Napoli, here is Salerno, and here is a Mediterranean Sea. And here is a famous volcano mountain, Vesuvius. And the ancient Roman city, Pompeii, excavated from below the volcano S 150 years ago, is here. So we applied this tour to this freeway of about 50 kilometers for two directions, for double directions. So that's the detector installation at the site. So far we have already considered about 42 kilometers, but for both directions. Then we will soon extend it to the whole freeway stretch. Yeah. And generally speaking, every morning a lot of people go to Napoli to work. So the congestion generally is created in Napoli and propagate along the freeway. But generally speaking, there is no congestion in the Salerno direction. Yeah. So as we see, that's the speed measurements in the Salerno direction. There is no congestion. Okay. But the speed levels are different from detector to detector. This means the freeway was quite inhomogeneous because due to the mountain, there are a lot of curvatures. There are some upgrade. So even without congestion from location to location, the free speed value are different. And this is the Napoli direction. Clearly, some detectors detected heavy congestion, dropped to almost 0. And these are some flow and the speed estimation results that I got 3 months ago. That's the flow and that's the speed. Okay, the estimation results looks very accurate. And I have already mentioned the original ambition for this work is to offer a kind of complete image of the real traffic situation that can be used by the traffic operator. So what's a completed image? The completed image is the following. Okay, that's the result shown by the GUI, by the user graphic interface of this tool. Actually, here we have, I present the two images of the GUI. The upper one, the lower one, okay, for the different moment. Here I explain the green color represent free flow condition, no congestion. And the red one represent congested condition. We also have yellow one, you will see later. That represents the situation between congested and the free flow condition. I want to mention all of those segments, okay, as we see, this is from one off-ramp. This is another on-ramp. So there is one link here. We separate the link into a number of segments. You see, each segment is marked with a green color, but it doesn't mean they have the same speed. It's just we have 3 categories. Anyhow, above 80 km per hour, that's free speed condition. This only means the flow speed here for each segment is above 80 km per hour, but doesn't mean they have the same speed. All the data can be real-time output to some data file. So the real speed for each segment can be checked by the traffic operator later if they want. But from the screen, we can see the general situation: free flow condition, dense condition, and congested condition. So, and each black node represent a detector. So this means we only have the measurements from the detector. All the other things are estimated. So as you can see here, early in the morning, there are some dense location, but there is no congestion. So now, as you can see here, the red curve represents the real measurements. The green curve represents the estimation for this location. So this means you see the speed dropped. That's the speed, because the congestion is coming. The speed dropped, then the estimation follows. Okay. So far, no congestion is measured at other locations. So no congestion is estimated in other locations. So we can see the congestion is here, is coming. Then with the time passing, here it already become very congested, and the estimated congestion shock wave keep propagate to the upstream. And here we can see, first of all, now congestion didn't reach here, right? So both measured flow speed and the estimated speed was high. Then now, with the congestion propagate to the upstream, this is the estimated results. Now you see the measured congestion already reached this detector, so the estimated congestion also reached this location, right? Then with the time passing, as we can see here the congestion was already dissolved. Here the congestion almost at the end was going to dissolve. The speed is going up. But here the congestion is going to reach here. So the next moment, indeed, the congestion already reached here, right? So what I want to say is the estimation results strictly follow the congestion propagating shown in the measurements. For example, what I want to say is the following. If here there is no congestion from the measurement, the red curve, you see the speed is 100 km per hour. If the estimation is already estimated here, if from the estimation we already see the congestion is here, but from the measurement there is no congestion, this means the estimator is doing work in a fictitious way. However, here that's followed correctly. The congestion is measured here, and indeed the congestion is also estimated around this certain location. And here we see there is no congestion because the speed is already going up a lot. Then the estimation result also going up. So the estimation result follows the measurements. And again, with the time passing, there is even the second congestion is coming. Okay, so we can see from this figure now there is no congestion, but next time moment the congestion already reached here, but which is consistent with the real measurements. Okay, so while this kind of comparison, we can see the estimation results somehow are accurate. So finally, then all the congestion was dissolved. Yeah. there is something interesting we can see here. Without congestion at this location, the speed measurement here is clearly lower than the speed measurement in other location. So then we check. We want to know why the speed measurement here is clearly lower. So we check the information from the site. We found out here there is no curvature, there is no upgrade, there is no tunnel, there is no lay job. So there is no reason for speed measurements here to be lower than other locations, but we just don't know why. So most probably this indicates a detector fault. When we use the real measurements, there are a lot of this kind of difficult situation we can handle. The measurements are never accurate. So the detector sometimes have problem. A certain detector has a problem. So this is could be the kind of measurement bias. So you see all this data, but we have to use them. So also 1 month ago, a German company, PTV, which produced the microscopic simulator vSim, they would like to use our tool for their work. So I did some testing for them. They gave us a freeway stretch example of 9 kilometers. So I got such traffic state estimation results. So as we can see, again, the measurement were not used by the estimator. So the comparison is fully objective. So for example, the serious stop and go behavior is estimated quite well. I think we don't have time to go to other simulation results, because so far I have only presented the real data testing results of traffic state estimation. But we have a number of other tasks. So far we don't have real data testing results. So I have a simulation example. Due to the time, I have already used 1 hour, 50 minutes. So perhaps I'm not going to the detail of the simulation testing results. Actually, I would like to mention recently we published a paper in Transportation Research Part C, which include all these simulation testing results. If you are interested in, you are welcome to read that paper, so that we can exchange our opinions. I would like to get your comments, remarks, and so on later via email. So, yeah. And we will produce such a tool. This tool has some major properties. It can handle a number of different traffic surveillance tasks under the same framework and in a systematic approach, unified approach. Also, this tool is a generic tool, which can be applied to the freeway network of any topology, size, and characteristics. It can handle measurements from detectors of different types. So far, our work of application of this tool to the Italy freeway is still underway. We haven't finished. So far, we only got the traffic state estimation results. They are interested in travel time prediction, for which we have to do traffic speed prediction. Yeah. Perhaps in the future, I will have another chance to present the corresponding results. And of course, this work was partially supported by the European Commission. We express many thanks. And thank you very much for attending this presentation. Yeah. And now we have the question time. Okay, please.
I guess my biggest question is, this is an elimination of sensors, or the need for sensors, and it's a cost-saving type of thing for cities, municipalities. What type of savings are actually coming out of the estimation model?
What type of saving?
Yeah, like how much money, or what kind of money is saved for a municipality?
You mean the quantitative criterion? So far, we haven't done so. For example, what we know is, if we check the literatures from the previous, for example, traffic state estimation is not new work. It means this work was already done since early in 1970s. But most of the work was done for a very short freeway stretch with a quite short detector spacing. If you check the literature, you will see normally they use detector spacing 1.5 kilometer, 2 kilometer, 2.5. I never see go above. I never see detector spacing which is bigger than 3 kilometer. For our work, the last test example, detector spacing is 7 kilometer. So at least we can save half number of detectors. So then it depends on how much one detector. Yeah. Not only like that. Detector, the price of detector is one thing. After you install it, because if you have a lot of detectors, at the side of freeway, there are some small house which provide the energy, the electricity to the detectors underground. Right? If you install less number of detectors, this kind of energy supply can become much less, and also the maintenance, right? So overall, how much can be saved? So far I can now say exactly. I suppose it's a lot. Yeah. Please.
What does your organization generally do with the results that you find? What are they used for?
You mean if I understand correctly, you mean what's the major purpose? Who would be interested in using this tool?
Yes.
Normally, traffic control centers. I mean, for each city, especially the big city, also the small city, they have traffic control centers. Sometimes they have two. One control center for urban traffic, one for freeway. So far, this tool has been designed only for freeway. You see, no traffic, no intersection, no traffic signals involved. So normally it's designed for the freeway traffic control center. Although you see, if you go to the traffic control center, they have a big TV wall. Each TV wall related to a certain camera. It looks a lot, but there are a lot of locations you don't know. The camera cannot see it. You cannot see it. So it's kind of a little bit of contradiction situation. On one hand, all of the information from the limited number of detectors is actually a lot. By eye, you cannot see. You have to set a person sitting there to see what happened at this location. This is tedious work. On one hand, it's a lot of information. It's already very much for manually management. But on the other hand, the information is not so much in terms of the spatial coverage. But it's only for some locations. But it's a lot for a certain location because the information may come every 1 minute. So on one hand, it's a lot. On the other hand, it's still not sufficient. Yeah. So normally it's used for them. So that's why we installed in the Napoli Traffic Control Center, Freeway Traffic Control Center. And in October, I'm going to the Antwerp in Belgium. They have the Ring Road freeway, surrounding the whole Antwerp city. They would like to install it. And also, for example, PTV company, they say they would like to apply it. They buy license from us. They would like to apply it to 500 kilometer freeway in Germany. I don't know where it is. It's too much. Because if they apply to 500 kilometer freeway, of course, the real-time property will become an issue. We have to update our tool. Real-time means once the data come every 1 minute, this means before next time the data come, you have to finish all the calculation. Otherwise, now the data come, then after 1 minute, the data come for the next time. Until next time, you are still calculating based on the data last time. That the real-time property is lost. Then this tool is a real-time application tool. Yeah. But if the freeway 500 kilometers, that's the calculations a lot. Yeah. We have to update in terms of the algorithm, software, everything. So far, we have to apply this tool to 50 kilometer, but double direction. This means 100 kilometer. 100 kilometers so far is good. With my laptop, I can run all the data for 24 hours. We need 5 hours. So this means real-time property is fine. This means if for 24-hour data we need 24 hours, this means just reach the boundary of real-time property. But now we need 5 hours. This means we still have a lot of margin to handle. This means if we apply to 200 kilometers, we hope we're still okay, but we are not sure. We didn't try because it's not linear. The calculation, the computational effort is not linear. It go up in the exponential way. So if you extend to 200 kilometers, it may already, the calculation time period. Yeah. Please.
How do you think that the information that's collected helps with traffic congestion, helps cities deal with traffic congestion and
You mean the
traffic accidents?
You mean the information? You said information collected. You mean the measurements collected, or the information delivered by the tour? Both.
Maybe I had a similar question. Maybe, and it's sort of following up, is if a traffic center is using this tool,
Yes.
and it's showing something on the screen,
Yeah.
output from the tool, then what do? How do they use that information? How do they respond to it?
How they use their information? Generally speaking, whenever we show this kind of tour to them, they are always feel very interested in. This means they need this kind of information very much. But I didn't really talk with them exactly how they use this kind of information. If I was a traffic operator in the traffic control center, at least, for example, I can see the congestion, estimated congestion is propagating from a certain location. Then normally I may give some alarm. Along the freeway. For example, I issue speed limit. For example, if I know the congestion is coming from the downstream, right, I will issue the speed limit from the upstream. So let the car to go slower than it should in normal condition. And so that because the congestion is coming from downstream, so you should not drive very fast just to knock the congestion. So this kind of thing would help smoother congestion. Also, if we know the estimation, from the estimation we know at a certain location, incident is already happened there. For example, in the freeway network, sometimes we have this kind of bifurcation. If I know some incident already happened here, I may apply so-called route guidance via the VMS to direct more car to select another way. Not to go to this way. Without such kind of information, normally, based on the current transportation mode, the driver rarely gets the real-time information from their car. So when they encounter the traffic congestion, when they encounter a traffic incident caused congestion, it's already too late for them to select another route. So if via the central system, all this information can be given to the central system, the central system can control it and direct more cars to select another way. So that's the way of use. So please.
I had a question. Is this something that in the future could be used to inform individual drivers in selecting their routes as they're on the freeway?
You mean is it possible to offer information to individual drivers via some in-vehicle equipment? Or?
Yeah, like an onboard computer in the future.
So far, this tool is only designed for use in the traffic control center. Of course, in the future, that's kind of ambition, not for us. That's an ambition of ITS. One of ambition, for example, in the future, every car would have an in-vehicle equipment. In front of you, there is a small screen which can show you the traffic situation, real-time traffic situation, like the complete image, which can update every 2 minutes, 1 minute, 5 minutes, can show you, taking you at the center, in the area with a radius of 5 kilometers, for example, in this area, which route is congested, which route is okay. In the future, this will be done. I mean, this kind of information, real-time information provision, so that you can make a decision by yourself which route to take. This can be done. Please.
We have a couple questions from the web, so I'll read you one of them. So, I guess. So have you given any thought to incorporating travel demand models to incorporate long-term predictability and assignments of different?
You mean traffic demand modeling? No, we haven't considered too much about this because this somehow is a short term. It's a real-time application tool. Demand modeling, that's focusing on long term, right? The demand modeling, more focusing on the long term.
I think the question is sort of in the network perspective, when a link's congested, about will people divert to other links?
The idea is following anyhow. The detectors for this tool, like the eye of the human. I mean, everything the tool can use is from the detector. So all the tasks are performed based on the real-time measurements. Of course, the real-time measurements may reflect the demand, may not. If it's in the early morning, if in the morning peak period, the flow measurements already reflect the traffic demand. But at the non-peak period, at noon, the demand the flow may not reflect too much. Yeah. But this work itself is not related to the demand modeling. Demand modeling is more for the planning purpose, I suppose. Yeah. Please.
So when you were developing this tool, could you just tell us a little bit about the process of testing it? As you were, how are you determining if it was accurate, if it was giving you accurate travel time estimations?
Well, for the travel time estimation now, we only have a simulation example. While the simulation, for example, from the simulation, you know what's the real travel time, right? The simulator will tell you. Then you can also estimate the travel time. You can compare how much is the difference. But in reality, that's different. It's not so easy to evaluate the travel time prediction. For example, you have to send a lot of floating car. You don't have such kind of car every day. We have to agree with the traffic control center. We say, okay, we are going to evaluate travel time prediction in this 1 week, in these 3 days. And these 3 days, they will send a lot of floating cars going around the freeway, then collect the information to compare with the prediction results. But then the key point is, without congestion, the travel time prediction is a trivial work. The key point is traffic control center would like to know under the traffic congestion, what will be the travel time. If now you leave from Portland State University for airport, but supposing congestion will happen on the way, then what will be once it happened, what will be the travel time of yours? This is very important. Without the traffic congestion, you can approximately estimate what will be your travel time. So the key point is under congestion. So whenever you send a floating car, you don't know whether that day the congestion will happen or not. Right? Sometimes we send a lot of floating car, but that day the situation was very trivial. Then the prediction result looks very nice, but doesn't say anything. Right? Yeah. So this had a lot of constraints actually. Yeah. Please.
Yeah, well, in case the traffic situation changes, how long does it take for the tool to adapt to new model parameters?
Yeah, this is a critical question. For example, I tested 2 cases, right? The weather condition. Under the weather condition, the free speed dropped, but it dropped in a mild way. It didn't drop like that, right? The snow doesn't become very heavy suddenly. At the beginning, it will be small and more, and the speed drops. So for this case, the adaptive, there is no problem. It's very quick. Yeah. For the incident case, there was an incident. Then, because when the car knocked, suddenly the capacity dropped, right? That suddenly happened at a certain moment. Then we estimate the capacity drop, the critical density drop. Then the question is, after the congestion was cleared, the flow was already going up. The speed was already going back to the normal values. How about the parameter estimation? We found out we need a longer time for the parameter to go back to the normal value. We need a longer time. It was not so quick. But on the other hand, there was no clear impact on the speed and the flow estimation. Although the parameter estimation was temporarily inaccurate, but this kind of inaccuracy that didn't have influence on the flow and the speed estimation. What I want to say is the major focus is estimation of flow and speed. The parameter estimation is just a mean, right? So although the parameter estimation was temporarily inaccurate, if it doesn't have clear impact on our major goal, that's fine. If it has, then that's a problem, has to be solved. This is what I found out. But we also have some explanation why, when the parameter estimation was not so accurate, the speed and the flow estimation was not impacted too much. We also have explanation. If you are interested in, we can. Please.
How do you determine how far the detectors are placed? Because you said 4 to 7 kilometers.
Yeah.
That's. I mean, what about the stuff that happens in the middle? You know, between 7 kilometers, they're placed.
That's another critical question. So we say our detector spacing is 4 to 7 kilometers. This kind of detector configuration work well if the congestion was coming from downstream. That's a pure congestion. If something happened, if the traffic incident exactly happened in between the two detectors, let's say 3.5 kilometer location, 7 kilometer, that's of course that's a problem, because until the impact of the traffic incident on the traffic flow dynamics reach the detector cannot measure anything. If the detector haven't measured anything, the tool cannot see anything. The tool cannot estimate anything. So of course there is a time delay. It means when the impact reached the detector, it was already some time after the accident, after the start of the accident. Then the trigger of the tool, the tool was triggered by this kind of impact, was also after the start of the incident. There is a time delay. The delay is depending on the distance of the detectors and depending on where the incident happened. Yeah, that's another. So nothing is perfect. If you install detector very densely, or whenever you have an incident, it's quickly measured by the detector, then you don't have problem. But on the other hand, if you have enough money, you do. Yeah. Please.
These situations along the freeway
Yes.
are detected, and the traffic control facility. The traffic control facilities, they obtain the information, and how quick is it to be relayed to private parties? And is there a sort of is that not available to private parties yet? And will it be in the future?
Not yet.
Okay.
Not yet, but in the future will be. But then in that way, the car has to be specially equipped with some machine, with some tools, or via a certain way. And the information can be given to the private, to the individual drivers.
Okay, and will that sort of be segregating more the upper class from the lower class then, if the lower class doesn't have the opportunity to obtain the tool to obtain that information for travel times and estimation times?
Well, that's more close to the economic and the political part.
I suppose.
Yeah. This one is another question. I have some doubts. I'm not sure. For example, now, let's imagine the current condition. Okay. Some car already equipped with such kind of machine. They already can get some real-time information. But imagine no car is equipped with such kind of tools. So no one can get the real-time information. So that's a current traffic situation. And we have congestion, we have so on, right? We drive. For example, every day we drive based on our daily experience, right?
Yeah.
If we are commuters, normally we know which way is the best from the home to the work.
Right.
Every day we took this way, based on our daily experience. You know, everyone drives in this way, and this way is efficient under the recurrent congestion. It means this congestion may happen every day. That's due to the demand. When the demand is higher than the capacity at a certain location, that congestion always happens there.
Okay.
So based on our experience, we can handle it without any real-time information.
So potentially.
But with real-time, whenever something special happened, the daily experience cannot handle it well.
Okay.
Because we don't have such experience, because the experience handles something which happens every day. Something happened, incident, for example. You never know where the incident would happen. The daily experience doesn't work well. If we still follow the daily experience, then the heavy congestion, is created, right? Because when the congestion happens there, actually we should choose another way which we don't use normally. But under this condition, it's much better. Since we don't know something would happen there, so we still do what we would do every day. That's how the congestion created.
Okay.
Now,
I'm sorry.
Sorry?
I just wondered if you would be broadcasting that via like the radio or via something like a personal computer program within the car or a personal computer.
I would say with a small screen.
Okay.
Which gave you the information that I show. Let's say marking the link with the different colors. So you can see which street is congested. Then you can make your decision in real time, right? But for me, it come out another question. If everyone has such information, perhaps the situation would be similar to the case everyone has no information. That's my question. So the best situation would come out in what case? 40% people have, 60% don't have. Then that 40% people will benefit a lot. If 100 people are with this kind of car, it's most probably it's like we don't have information at all, because everyone knows there's better, so let's go there. Then a lot of people go there, then the other street become much better. Then the whole networks just become like under such oscillatory situation. Here congested, a lot of people rush to there, then there congested. So I believe this kind of information provision is not the best way. Also, it's only good for the people who are familiar with the city. If I just came to this city one day, even you gave me a lot of information, I still cannot make a quick decision. Should I stop the car at the side and looking at the window to think which route should I take? Right? It's only useful for the commuters. It's not good for the really good. So we prefer to take the route guidance way. Meaning we don't give information, we give direct route recommendation at a bifurcation node via VMS. I don't tell you which way is shorter. I say when you reach the bifurcation, if you want to go to Paris, please take this way. If you want to go to London, please take this way. So you don't have to know why, because all the calculation is done by the higher level traffic control center. It just gives you direct route guidance. I believe this way is much better. I mean, not to ask each individual driver to do the decision. The overall outcome of this kind of individual decision may not be good. That's what I believe. You're welcome. Please.
So I think one last question.
Are there any other inputs to your model other than flow and occupancy measurements?
Input normally so far actually we only use the flow and the speed. We even didn't use the occupancy. Yeah, because the three variables, the occupancy actually correspond to the density, right? Flow, speed, and density, these three variables are not fully independent. Once you know two, then you know the third. So we believe only two kinds of measurements are fine. And also the occupancy is much more related to the effective vehicle length. So it depends on how you tune the detector. We believe the occupancy measurement are not very accurate. We think flow and speed measurements are more reliable. Yeah.
So, before we thank our speaker, thanks to all of you for the good questions. Next week, Professor Lei Zhang from Oregon State University will be presenting the future of advanced travel demand modeling. So we look forward to seeing you then. So let's thank Dr. Wang for his presentation.
Thank you very much for attending. Thank you very much for such an opportunity. And thank you very much, Professor Bertini. Thank you very much, Professor, Jennifer. Yeah.